What that means, really, I always want to say it with a picture, too. What does it mean that so let me draw two orthogonal directions. I won't make them, I intentionally didn't make them just x and y axes. This might be the direction of sine x, and this might be the direction of sine 2x. And then I have a function. And I'm trying to find out how much of sine 2x has it got in it, how much of sine x has it got in it, and then, of course, there's also a sine 3x and all the other sine kx's. The point is, the point of this 90-degree angle there is that if I can split this s of x, whatever it might be, I can find its sine x piece directly by just projecting it. It's the projection of my function on that coordinate. If you don't like sine x, sine 2x, s of x, write v1, v2, whatever, to think of it as vectors. What's the sine 2? So that is b1 sine x. That's a certain that's the right amount of sine x, and the whole point is that calculation I did not have to do. It didn't involve b2 and b3 and all the other b's. When I'm projecting onto orthogonal directions, I can do them one at a time. I can do one-dimensional projection at a time. This bk, to say it, bk sine kx is so I'm just saying this in words, is the projection of my function onto sine kx. And the point is, I could do this and get this answer because of that 90-degree angle. If I didn't have 90 degrees, do you see that this wouldn't work? Suppose my two basis functions are at some 40-degree angle. Then I take my function. Can I project that onto this guy and project that onto this guy so that the projections are there and there? Do they add back to the function that I started with, the given function? No way. I mean, these are much too big, right? If I add that one to this one, I'm way out here somewhere. But over here, with 90 degrees, these are the two projections. Project there, add those two pieces, and I got back exactly. I just want to emphasize the importance of orthogonality. It breaks the problem down into one-dimensional projections. Okay, so here we go with bk sine kx. Okay, let me do the key example now. This example. Let me find the coefficients of that particular function s of x. This is the step function, the square wave s of x. Let's find its coefficients. I'll just use this formula. Okay. Maybe I'll erase so that I can write the integration right underneath. Okay. Oh, one little point here. Well, not so little, but it's a saving. It's worth noticing. It's the reward for picking off the odd function is, I think that this integral is the same from minus pi to 0 as 0 to pi. In other words, I think that for an odd function, I get the same answer if I just do the integral from 0 to pi that I have to do, and double it. So I think if I just double it, that's I don't know if you regard that as a saving. In some way, the work is only half as much. It'll make this particular example easy. So let me do this example. What are the Fourier coefficients of the square wave? Okay, So I'll do this integral. So from 0 to pi, what is my function from the graph? It's just 1. This is going to be a picnic, right? The function is 1 here. So s of x is 1, so I want 2 over pi, the integral from 0 to pi of just sine kx dx, right? Which is, so I've got 2 over pi. Now I integrate sine kx, I get minus cosine kx, right? Between 0 and pi. And what else? What have I forgotten? Most important point. The integral of sine kx is not minus cosine kx. I have to divide by k. It's that division by k that's going to give me the correct decay rate. 2 over pi k. All right, now I've got a little calculation to do. I have to figure out what is cosine kx. At 0, no problem, it's 1. And at the other point, at x equal pi. So what am I getting then? I'm getting 2 over pi. And this one is, no, 2 over pi k. All important, pi k. With that minus sign, I'll evaluate it at x equals 0. I have 1 minus whatever I get at the top, cosine of k pi. That's bk. So there's a typical, well, not typical, but very nice answer. Now let's see what these numbers are. So let me take a 2 over pi out here. And then just list these numbers. At k equal to, so k is 1, 2, 3, 4, 5, right? Just tell me what these numbers are for, let me put the k in here, because that's part of the, so it's a constant, 2 over pi. What is, at k equal 1, what do I get? At k equal 1. This is now, this is the little bit that needs the patience. At k equal 1, the cosine of pi is negative 1. So I have minus 1. I get a 2. I get a 2 over a 1. K is 1. All right, this is the coefficient for k equal 1. Now what's b2, the coefficient for k equal 2? I have 1 minus cosine of 2 pi. What's cosine of 2 pi? 1. So they cancel, so I get a 0. There is no b2. What about b3? So now b3, I have 1 minus the cosine of 3 pi. What's the cosine of 3 pi? It's negative 1 again, right? Same as the cosine of pi. So that gives me a 2, and now I'm dividing by 3. 2 over 3. All right, let's do 2 more. K equal 4, what do I get? 0, because the cosine of 4 pi has come back to 1. So I get a 0. And what do I get from k equal 5? 1 minus the cosine of 5 pi, which is back to, cosine of 5 pi is back to negative 1. So 1 minus negative 1 is a 2. You see the pattern. And so let me just copy the famous series for this s of x. This s of x is, let's see, the 2's, I'll make the 4 over pi, right? I'll take out all those 2's. So I have 4 over pi sine x. I have no sine 2x, forget that. Now, I do have some sine 3x's. How much do I have? 4 over pi sine 3x's. But divide by 3, right? And then there's no 4x's, no sine 4x's. But then there will be a 4 over pi sine, what's the next term now? Are you with me? So this is a typical, nice example, important example. Sine of what? 5x divided by 5. Okay. That's a great example. It's worth remembering. Factor the 4 over pi out if you want to. 4 over pi times sine x, sine 3x over 3, sine 5x over 5. It's a beautiful example of an odd function. Okay. And let's see. So what do you think? MATLAB can draw this graph far better than we can, but let me draw enough so you see what's really interesting here. It's interesting and famous. So the leading term is 4 over pi sine x. That would be something like that. That's as close as sine x can get. 4 over pi is the optimal number, the optimal coefficient, the projection. This 4 over pi sine x is the best, the closest I can get to 1 on that interval. And now, but with just sine x. But now when I put in sine 3x, I think it'll do something more like this. Do you see what's happening there? That's what I get with sine 3x, and of course odd on the other side. What do you think it looks like with sine 5x? You really have to, it's just so great, you have to let the computer draw it a couple of times. You see, it goes up here, and then it's sort of, you know, it's getting closer. It's going to stay closer to that, but I don't know if you can see from my picture. I'm actually proud of that picture. It's not as bad as usual. And it makes the crucial point that, two crucial points. One is, I am going to get closer and closer to 1. These oscillations, these ripples, will be smaller. But, here's the great fact, and it's a big headache in calculation. At the jump, the first ripple doesn't get smaller. The first ripple gets thinner. The first ripple gets thinner. You see the ripples moving over there, but their height doesn't change. Do you know whose name is associated with that phenomenon? Gibbs. Gibbs noticed that the ripple height, as you add more and more terms, you're closer and closer to the function over more and more of the interval. But so the ripples get squeezed to the left. The area under the ripples goes to 0, certainly. But the height of the ripples doesn't. And it doesn't stay constant, but nearly constant. It approaches a famous number. And of course, we'll have the same odd picture down here. So, and it'll bump up again. It's the same thing is happening at every jump. In other words, if you're computing shocks, if you're computing airflow around shocks with Fourier-type methods, Gibbs is going to get you. You will have to deal with Gibbs because the shock is not, the shock has that extra ripple. Okay, that's a lot of section 4.1. Energy we didn't get to, so that'll be the first point on Friday. And I'll see you this afternoon and talk about the MATLAB or anything.